The community, so you have all the big players that are pushing forward OpenStack. Over the year, Huawei has invested more and more resources on the development of the platform. I put here the latest ranking. I think it was from a couple of weeks ago. Red Hat, the first one, we ranked second, Rackspace, IBM, and Huawei. So it's the number of reviews, contributions that you will see within the open source platform. So our problem is the following. So the platform being supplied by OTC, it has this OpenStack management layer. The platform is much larger because, depending how you look at it, OpenStack may have 20 million lines of code. The system that make a public cloud has far more than 20 million lines of code. So you need far more logic. And one of the problems that we have is when we have a large platform and the data center has 50,000 servers. And when you have 50,000 servers, what will happen, and I did try to do the numbers so you can see how much data we can generate per day. 50,000 servers with 30 plus services, and you can have even more services running here in this infrastructure. And that's approximately 80 billion logs and monitoring data per day, so that's 40 terabytes. Processing 40 terabytes of data, it's a lot. We don't do that, it's too much. It's too much data and too much noise, because this is all the information that you can generate. Well, everybody likes to look at these large numbers, and we don't like them too much, because when they get large, we get a huge problem. So we follow an approach which is slightly different, is, well, we are happy to have the 40 terabytes, but we would like to have some structure into this information. The information on these logs, we don't want to log information which is done into a file. This is very hard to parse and very hard to take decisions. So I will show an approach where we try to bring some structure. And this is related to the notion of models. But we do the opposite. I was listening to your presentation this morning. I realized that actually we do the opposite. We don't design models. We create models based on what happens. Because I will just go forward. I will come back to the model analogy and comparison. So cloud operations, how do you operate 50,000 servers? So when one server fails, what do you do? Now, if one server fails, this is very lucky, because if they fail, usually if it's a clear fail, the platform will just move forward. So the host will be removed, not physically, but logically from the platform. The problem is the ones that are very, very fine-grained. So you see some servers slowing down, and you don't know the reason. And those are hard to detect. Why? Because it's not a clear code. It's slowing down. The requests are slowing down from the customer side, but the platform and servers are working fine. And it's hard to detect those things. This is one type. The other one is correlation. So when one server, the behavior of one server may affect the behavior of other servers. Or when you have 10 servers handling a request, and one of them is the one that has a fault, but it can somehow be compensated by another, speed-wise. So this is where we want to have more insights into a platform. Nowadays, the most advanced techniques, usually they do log analysis. So you have, everybody has logs, and the ones, researchers here that work with Unix know that a little bit better. You have usually a log directory, the applications will just dump information. This information is useful, but usually you have humans actually going over that information. You have some companies that specialize in string pattern matching over logs, give you some information. But this usually it's not sufficient. So we would like to have more data. So we come into the, sorry, could you please go back? We have this analogy where you have two problems. As the data centers get bigger, and here we are here with 50,000 nodes, you have two problems that you need to solve. One is the scale, the other one is the complexity. Now the scale means you have 50,000 entities to manage, so this is a lot. And the second part is the complexity. So for the first one, you use automation. So you have a lot of scripting languages and approach, which you can apply the same recipe over and over again. The second one is the complexity, how do you handle it? So what we would like to do is to start using intelligence, AI, and I will show you that others have already started to do this. There is So I will just move forward. Cloud operations. So these are some of the use cases. I will just ask you to look at the first one, anomaly detection, because it's the one that I will talk more about, and since our time is a little shorter. Just keep in mind that we'll be trying to detect anomalies within 50,000 servers. The second part that I like to mention is this one. This is a work from Google. They published a book last year, in April, if I'm not mistaken. It's called Site Reliability Engineering. The book is very well written. It's engineer-oriented, but it gives you the motivation, gives you some solutions, how Google is managing and everything. So we know that when they publish such a book, they are already doing something else, because they move forward. We know that, but it gives good examples of the open source that was developed as a result of the experience from the management, all the strategies to use time series analysis to monitor the services, the challenges. It's for those who have interest in this type of work, I would recommend Google's book, Site Reliability Engineering. Here, you will see some of the parts that we are also looking for. For example, one way to detect if your platform is about to have problems is to look at latency. So problems, they start with latency problems. The server will not fail, but it will start having latency problems, and a few hours later or a few days, it will fail. So we want to look at latency. Errors, also not as much, because this has been done for quite a few years. It's helpful to combine with latency analysis, but for error, basically parsing logs, trying to look for messages with the keyword error or warning. We have good solutions that will be developed by many companies or many papers, so this is quite understood. And saturation, we don't really look at it right now, but it's also interesting. So we will concentrate on anomaly detection and latency. Things get slow. Cloud operations, using AI, other companies are looking at it. I will maybe start, I will not go over all these companies, I will just give you examples of the one that I found more interesting. I like the approach from Microsoft. Azure, it's their public cloud platform, so number 2 worldwide. And they start already to provide smart detection, failure, to detect anomalies within their cloud. It's slightly different from what we are doing because they are providing the service to customers. So if you develop the cloud-native application on top of Azure with, let's say, 50 different microservices or services, they are already providing to you solutions which use AI to detect problems within your platform, or let's say, within the system that you are in. So they bring this to the user. We don't bring it to the user. In our case, we actually study the underlying platform. So if you will, Microsoft supplies a solution to customers when they develop 50 microservices together, and we are looking at the 50,000 physical servers that are actually providing this service. I like Salesforce. Actually, this table comes from Salesforce. There was an article in ACMQ in April this year, a couple of months ago, and they were discussing their work on bringing AI to operation. So at the beginning, everything was done by humans. DevOps, we start replacing some human activities to machine activities, and they come up with this term called no-ops. Others call it AI ops, but the objective is the same: bring AI to the operations of a data center. We only tackle those two here, so the presentation will be about those two. Distributed tracing. This is a technique that we use. I think this is a very interesting technique, and it's easy to implement. And the results, what you can get back, is huge. So this is the way I see this distributed tracing approach. I will give you an example. This is OpenStack, so you can have between 200 and 20 million lines of code. And OpenStack enables you to create virtual machines. So you go to the command line and you say, well, I would like to have a virtual machine. And the system composed maybe 50 physical nodes if you have a virtual infrastructure. will coordinate efforts to provide this VM. And you'll have several physical nodes and several services running on the physical node trying to give you this VM. And what tracing enables you to do is to trace this request. And we already heard today this notion and this importance of tracing. So it enables you to trace the request. So here, as you see in these vertical lines, you have different services. All those are different services that may be located in different physical machines. And each time, in our case, what we do is each time a user issues a comment, we have one picture of this that comes out automatically. So if you do anything with the OpenStack as a distributed system, we will know exactly how the comment was executed. This is so this is generated automatically. We don't do this manually. And this is the notion of model. We don't know the model. We will know the model when we see it. And it's curious because OpenStack has 20 million lines of code, and you would assume that developers have developed a lot of models first. They have discussed the models, and when they have agreed on the models and do some correctness checking, and then they went to the implementation. As a software developer, if you have a PhD, I'm sure you will do that. But if you are a software developer, hardcore software developer, you don't do that. You will discuss the model with bullet lists. So you will get in a session with remote session with other developers. And with the bullet list, you have your model. And that will be the sequence diagram. The bullet list will tell you the sequence of interactions. And then you have another bullet list about the class. So that the class will have A, B, C, or D. And at the end, you don't have this type of models. You have text-based description. And the problem is, when you want to understand how such a system works, you don't even have documentation. So what you do, usually you spend literally a month going through code, trying to reconstruct this model. And via what's called distributed tracing, what you do is a very simple technique where you know the trace or how a service request is handled. And you go through all the code at specific points in the code, you do instrumentation. So you make some calls to an Excel system and will notify an Excel system have reached state A, have reached state B. And with this sending of events that describe the state of the distributed system, you can then reconstruct this type of structure. Things that you do not see because it's too small here, you have the timing, so you know if a call has taken more time or less time than usual. This is one way to do a documentation. You don't see it also here. You have the parameters, you have the services, you have the IP of the machine, you have the memory available when a machine handles the request. And this correlation of events across machines is what gives these techniques a lot of potential to do a better anomaly detection, among others, to the example. So what we do is first we trace a request, so we put these instrumentation points inside the code, so we need to change the code. If you're lucky, the code always already comes with instrumentation. It's possible. A lot of companies are moving into this direction. Huawei is moving into this direction, so the code will already have instrumentation points in the future. If you do not have that, you have to do it by hand, which is somehow costly, but then it's a decision of the platform. Each time the code is executed, you'll get these traces. I will give you an example later. And with these traces, which are just messages sent over message queuing systems, and then processed with streaming. And if you want things to be done fast, you get this diagram. Once you have this model, sequence diagram, you can just do the analysis of the platform and see if things are getting faster, slower. It's a little bit more complicated than it seems. But you can study time drifts, and you can study structural changes on the way the platform is moving. Distributed tracing, the most well-known case I would say is Google, Stackdriver. So they actually have a service now, Stackdriver. It enables you to do tracing. They come up with tracing between 2000 and 2010. We don't know exactly when. We know that their paper was published in 2010, and that has triggered a lot of companies, open source, to follow this instrumentation. Amazon, curiously, was really surprised in January this year, they launched their X-ray system, and it was a few months ago still in beta, so you could try it, but you could not evaluate it. And they bring also this type of tracing into a cloud-native application. So we know that we have several companies moving in the same direction, and we believe that it's something interesting, especially also for universities. Universities, they have far more resources from the analytical side, and to think about this how to use tracing information. Not as building the infrastructure, because this we can build, this is not a problem for us. What we have difficulties then is when you have 1 terabyte in one hard drive of tracing information, how can you detect that you have a problem in one machine? Distributed tracing, again, I will skip it. This is just OpenStack, and you have a request from the user, and you have all these services that will be invoked with a certain sequence. And all of this generates something very important, which is this. This is a sequence of events. This is what's important for the analysis. You have A, B, negative B, negative A. It's negative just because of the format that we use, not the why. I call them negative, they have a number. And this is a stream of events. The question now is, when you see a new stream of events, is this stream a normal stream or an outlier? It's a simple question. How do we do tracing? So this is back to the question of the models. Do we have the models? No. So people, software developers code like this. So this is OpenStack. So this is the system. This is a command line interface. If you install it in your laptop, you can use it exactly the way I did. Just write OpenStack, a server create, you pass the flavors, the operating system you want to use, and the network where your VM should be attached. And you have all these happening. So you have a call to get a authentication token. So it goes to a specific service to get a token. You get the token back or not, but if you get it back, you use the token to resolve your flavor that you are asking, and you use the token to also resolve the image in case you have specified a name. When the system has all this information, what it's going to do is will actually contact this service here, another API, and it will pass on this information for VM to be created. So in this slide, we are in this state. Now, once again, the model we don't know it. Only if you study the code, and this is you will know it via instrumentation, okay? Because then you have an image that will show you what type of model you have. So you go through the codes, and this is extremely difficult. And I was trying to, this morning, to find about an analogy. Why is this so difficult? When you see it in the slide, it's really trivial. You just go through the functions that are invoked when you are creating. The problem is finding the sequence of the function. And this is difficult. And I was trying to find an analogy. Going from Lisbon to Munich, it's easy. Why? Because usually you have directions. You have an arrow that says, well, you can go to Port. And then to Port, you have an arrow that says you can go to Barcelona. And you follow all these paths, and you will go to Munich. Now imagine that they will place you in Portugal, and they will remove all the indications, all the arrows, and they will ask you to go to Munich. You will go everywhere in Europe until you find the right place and the path. And here the same thing is 20 million lines of code, and you don't know which ones are being invoked. So usually you go really step by step. So you create a VM, and you try to go through the logs to see where is the name of the VM you just created in the logs. And you find the name that you have used, which is unique, like XYZ123. It has been registered in some log of some service. So you know that that service was invoked. So then you go through the code of that service, and you put a lot of printfs. Not printfs, but it's something similar. And eventually you will see what was the method that was called in answer to this request. And this will take you a lot of time, but eventually you will get the solution. It may take you easily 6 months to understand how OpenStack works, and you will probably be only looking at how to create a VM. You will not be looking at everything that you can do. So this is why instrumentation is tricky to achieve it. It has to be generic. So you need to place instrumentation points in generic places that are used by the implementations. So you do this. Next slide. You do this again, and you start reconstructing this. And here, on the left side, you see the different functions that can be called, and here I place dots that are red that show you that Nova API and has contact with the conductor via RPCs, so it's a different service, another server running. And the conductor has issued an RPC call into the scheduler to decide to which host will actually create the VM. And then you will send an RPC to a compute node, telling the compute node to actually start the VM, and the compute node will call the hypervisor that will actually create the VM and then send the information. So with this type of approach, you have several tracing, several advantages. You reconstruct automatically the model afterwards, not before, but afterwards. But for us, it's a big. This is again the sequence of events, and here this is one event. So this is what's generated in one instrumentation. So when you do OpenStack create server, the VM will be created. But first, a request will go to the identity management to get a token and to authenticate your password and all. And this will create two messages. Obviously, depending on how many instrumentation points you want to place in the system. And when then you go to the conductor, you call the conductor because you want to do an operation over a database, another message will be there. So they always, in this case, they always come in pairs. That's why you have big and negative. And this is one of the messages. We use JSON. This is not anything specific. And you have information related to the trace ID, for example. The trace is a long sequence of messages, so it's a stream of messages that are related. The host that has processed the request, the time that has elapsed in the beginning, this time is very important for the time series analysis. The IP of the machine, you have the method that was being called, the path. Let me see. Here you have the name of the service that was called, the parent of the trace, if you have hierarchies of traces. The project, which is a big component of OpenStack, so it's called Keystone, and the service was called admin. You have the timestamp and the trace ID. You can have more information, so I'm just giving you a small extra. But there is always a trade-off. You want to have a lot of information, but if you place too much information there, you have delays. And the delay, if you start keeping traces with a lot of information, there is a large penalty into OpenStack. It means that instead of giving you an answer within 400 milliseconds, it will take 800 milliseconds. And we saw yesterday a presentation on slightly different, but Amazon for each 1 millisecond, for each 1 millisecond that Amazon takes to answer to a customer in the web page, they will lose 900 million. Is it 900 million? It was a huge number. So when you have these traces and you have this sequence of events, a stream, and they all have this information, you can do anomaly detection. So basically you take a stream and say, well, is this stream sequence of events something normal, or it has a strange sub-patterns? And this should be flagged as a pattern. Service relationship analysis, this is related to the models again. You have, what we see here is one trace, and Frank this morning said, well, this is one instance, it's true. If you put back together all the instances, you get the model, the behavior of the system. And you can do this reconstruction of how OpenStack works, what is the model behind the complex system. Service time analysis, this is related to the time series analysis, so you look into time, and you see if you have deviations. And the platform stability analysis, we here talk more about forecasting. So if you see a trend of change time-wise, so things take every hour a little bit more. And if you can identify that this trend is always going up, you know what will happen. So this is the overall approach. In practice, it's a little bit more complicated because you have the last slide will kind of explain to you why it's difficult. This ends up being difficult in practice to achieve. Machine learning for ops, so we do things. This is again a simplification of what we do, but I think it gives the idea. We get a lot of traces, and we use clustering, for example, and we cluster traces. So some traces go to the extremely performant traces, some go to the bad of the traces with problems, and some go to the average traces. And when we have these clusters, we can then detect outliers. Here it's also another technique to detect outliers. We are very, very lucky because Python, it's an example, Python has a lot of libraries, so we like to put in Python because of the libraries for machine learning, for time series analysis. We also consider going into R, and we also have packages, but you can typically achieve this type of results very quickly. When you want to improve the performance, that's when it becomes more complicated. And once again, the last slide, I will try to explain to you why it's the case. Trace mining for ops, I don't call it process mining because we don't really have this notion of complex processes. We have traces and sequences of events. But we are looking into some of the work that is being done in the community of business process modeling, specifically process mining, and a lot of things can be reused. So they have to be reused and tweaked a little bit, adjusted, but a lot of those concepts. For example, this one, which is a very simple way to reconstruct such a graph based on simple traces. So imagine that OpenStack handles the service request and throw out one of the graphs that you see, which is a trace. So this is one of the instances, this is another one, this is another one. What we would like to do, for example, is to reconstruct the full model of the working system. And here again, it will be interesting because we don't start with the model. We start with people that do whatever they feel that they should do. And at the end, we give them the model explaining how the system works. This is a side effect of our research. We are not into giving documentation to software engineers, but it's something that at the end we can also use. Talking about software and modeling, it's also interesting because, in fact, some people start with the model, the document. The document is valid because a lot of processes inside companies tell developers you have to provide the architecture and the first code. And they will provide the architecture. Now, the architecture, a colleague of mine, the first question that he asks usually in meetings is, does the document with the architecture and the modeling matches the system? And most often is no. It was done at the beginning, it matched then, not when the system is finalized and delivered. Then it doesn't match, I mean, just works. This is also time series analysis, so this is something that we did just as trying to explain how easy it can be to detect deviations on traces. This is maybe hard to explain. This is A and B happen, one after the other, and they have a duration between the two. It's a little bit more complicated because this duration includes network time and compilation time. But at the high level, it's a duration between two events. And what you can do in simple terms is use stream processing. You process the stream, and you try to compute the time, the weighted moving average, and you try to find boundaries based on the deviations. So, this is done for many years, so it's not something that we introduce. So this type of problems exist for many years. And what you can do is, if you have the day of the month, you can have graphical representations where you compute what is the deviation based on the normality of my trace day number 1, 2, 3, 4, 5, 6. And you just detect how much is the deviation. This is not the actual time, it's just a deviation. And then you just have these thresholds that will tell you if the platform is getting slower. Similar, on the top you have the trace, you have the events, you take D and D negative, you compute the duration of the time that went from D to D negative, and then you try to extract the actual duration by removing, for example, seasonality to identify, for example, the trend and having the remaining zero. This, again, ARIMA can be used, so those are known methods from statistics. Nonetheless, most of them needs to be calibrated. Doing this, it's easy by hand, so you can do it. So you just look at the signal, and you start adjusting, you remove the noise, and then you do it. You do it in Python or in R. It takes you 4 hours, and you can actually analyze the signal. Here, the challenge, how do you make this automatic? You cannot customize a solution for a signal that happened last week. You need to have this set of techniques that you will put together that will try different models and different parameters, so that at the end, automatically, the system will give you an answer. And this is what we are looking at, how can we achieve this solution. We can move to the next one. I will just go probably to the last slide. This is the last slide. Why it is difficult to achieve this trace analysis and using machine learning? Because what will happen to your traces, it's easy to understand when it's only time. So a computer is a little bit slower, it will take more time, and the trace will expand in time. But the problem is the traces will reflect the architecture of your complex system. So everything that was designed within your distributed system, you will come in the traces. And knowing if a trace is valid or not depends on the architecture of your distributed system. So obviously, I will give you maybe an example, which is easier to understand. There is something called very simple, which is the retry pattern. One service cannot contact the other one, and by configuration, it will try 3 times with an interval of 30 seconds. Which means that you may have a new trace of a behavior which is accepted by the system. So now you have a sequence of events that show up in a trace, which is the retry pattern, and A negative will show up duplicated 3 times. And this, in a normal, let's say, system or approach, we would say, well, it's an anomalous trace. This is not accepted by the system. But in this case, it is accepted by the system because it's a function of the system. And if you don't know the function or how the system are designed, you cannot debug the algorithms. And for this, you have a lot of, all those are actually examples, the cold hard problem. If the platform is not answering any requests for 20, 30 seconds, so it's a public cloud, and if some parts of the cloud are not working, it will go to the cool down, which means that caches will be made invalid, which means that when the platform answers again, you have traces that will be different. It's not that they are invalid, it's just because the system moved to a specific state. Load balancing, high availability, elastic scaling, all those are properties of cloud. So this is what you encode into your system, and all those will make the traces change. So this means that all the algorithms, or many algorithms that you have from statistics, they will fail. As long as you don't have these patterns or this behavior of the system reflected into the traces, you can probably use normal tools. When you start having these implications into your systems, that's when you will have stuff. Just to close, because my time is over, and as a motivation, I will try to explain that log analysis has been done for more than 30 years. You have very good tools. They are all based on one principle. You can do string pattern matching over logs. So you have logs that take maybe 1 gig, and you just try to find within 10 messages if you have the keyword error and warning. And if you have, you say, well, I have a problem. Or you use a graph over the days, and over the days, what you do is you have a bar that says how many errors and warnings were seen in the logs, and in which physical server you have these logs. And this is the best that we had so far. It's very hard to interpret those logs because the logs, the messages come from developers. Developers are writing code, they write messages not for the operation team, they write messages for themselves. So which means that then we are using those messages actually to do something different, which is the operations and the anomaly detections. So we start using natural language processing, which try to use statistics to infer that the message most likely is related because the tenant is the same and it was within 100 milliseconds. So you start reconstructing a model which is it's not correct in some parts, which you don't know which ones. You have probabilities in it, and then you try to extract some information. Tracing solves, let's say, this problem, because the trace and the correlation of events comes from the distributed system. And we believe that this is something interesting, so we are collaborating with TU Berlin and also the University in Munich. And we believe that universities and academia can give us a hand to solve this problem. Thank you for listening.
We are open for a few questions. Yeah.
I'm wondering if some of the challenges can be solved by annotating trace records with appropriate metadata, like identify the read drive, it happens by having an instrumentation point telling that this is a read drive, or is that not an option?
I think it's possible, but then what I would suggest is to build a system that looks at the code and finds those patterns to tell me where should I place the instrumentation point. Because it's true, the annotation would help. But then I still have a problem, which I would like to minimize, is to go through the code and say, oh, here there is a retry pattern because I have, 4 cycle and I have an RPC call, and then I have failure, I will retry, and it's linked to a variable in the configuration file that sets the time to 30 seconds. So as a human, I can do this, but this will take me a lot of time. But if you could come up with a solution that analyzes the code and one sees these patterns, which would be well known and described, and to say, well, here is probably a very good place to place this annotation of a retry pattern, then it will definitely help.
More questions? Okay, so I would like to close the session over here and thank the speakers as well as the audience. Have a nice lunchtime, and we resume here at 3:30. Thank you.
Everything was.
Yeah. Oh, now we have two. Where's this one? This is yours, right? And then this one is reading your computer. Could you see the sticker of him? Or ich habe meins, ja. Good.
This way?
Yeah. Bitte?
Ich habe eins, das sieht genauso aus.
Da müsst ihr gucken.
Das ist deins hier, aber es passt nicht in meine Höhe.
Okay, dann müsst ihr
Deswegen
gucken.
hat das auch nicht funktioniert.
Genau, das ist die richtige. Ja.
Okay.
Guck mal, das, was du jetzt gegeben hast. Ich bin mir nicht ganz sicher.
Das ist deins.
Du meinst, das Ding, was drin ist, irgendwie.
Das probieren wir jetzt gleich, aber ich glaube, das ist deswegen funktioniert.
Ja, genau.